Now, in this example, you might be wondering why I did not include the gravitational potential energy in mass 2 in the solution. At least you should have been. So why did I not do that? Let me show you why. Now, let's assume a mass spring system, simple, just K and M in vertical orientation. And this is the undeformed position, and when the mass is slowly released, it will move and stay at what we call the equilibrium position. And it will remain at this position. Now, let me try to derive the equation of motion of this system once measuring x from the undeformed position, and then in the second approach measuring x from the equilibrium position. Now, the difference between the two positions is delta, which is the static deflection. Delta is the static deflection, and obviously K times delta is equal to mg. Now, first, let's try and start deriving the equation of motion with measuring the motion of the mass from the undeformed position. First, I will determine the kinetic energy term, which is 1 over 2 m x dot squared. And now, if this is x, the potential energy equals, in the spring, the total deflection is delta plus x. So the potential energy is 1/2 k delta plus x all squared, and then including the gravitational potential energy, the mass will drop a distance x plus delta, so it's negative mg x plus delta. That's the gravitational potential energy. Now, the Lagrangian obviously is the difference between the kinetic energy and the potential energy, which is 1/2 mx1, it's just x dot squared minus 1 over 2 k x plus delta squared plus mg x plus delta. Now the partial derivative of the Lagrangian with respect to x dot is just the first term, which is m x dot, and its total time derivative d by dt partial L partial x dot equals m x double dot. Now the partial derivative of L with respect to x is, I have here negative k x plus delta, and the derivative of the bracket with respect to x is just 1, plus mg derivative of the bracket is, with respect to x, is just 1. Okay. Now, expanding the terms, we get negative k x negative k delta plus m times g. But mg is equal to k times delta, so I can cancel mg and k delta. I will end up with only negative k x. So even when I included the gravitational potential energy, when I started from the undeformed position, the gravitational force mg cancels the initial deflection or the static force in the spring, and I will end up with only the terms including x, which is starting from the equilibrium position, which tells me that every time I have a mass in the system where its weight is supported by a spring, I can ignore the gravitational potential energy, and I will just measure x starting from the equilibrium position. That's only when a mass is supported by a spring. Now in this example, M2 was supported by spring K2 and in series spring K1. And when X2 and X1 are the equilibrium positions, we start the measurement from the equilibrium position, then I do not need to include the gravitational potential energy of M2 because it's balanced by the force, the initial deflection force in the spring.